and change the camera and start recording. Perfect. Now, the few questions I want to ask just briefly. How does a deadlock happen? Okay, no, you don't have to worry about it. How does a deadlock happen? If four conditions happen in the system, what are they? Name one of them. Great. Mutual exclusion. Second condition. Pardon? Non-preemptiveness. Right. Condition 3. Circular weight. Condition 4. Hold and wait. If those four conditions occur in a system, we're going to have a deadlock. Now, how do we avoid a deadlock? Using Banker's algorithm. How do we prevent a deadlock? Eliminate one of the conditions from a system, and that would be a prevention of deadlock. How do we detect if there is a deadlock in a system? Using that resource allocation diagram that we used, right? Okay. What I'm going, yeah. What we're going to be talking about today is another problem that's caused by multiple processes executing simultaneously. In a system, and it's not deadlock. This time, we're not looking at the processes themselves. We'll be looking at we're not looking at the resources as such. We're looking at the processes. So, if we have multiple processes running in a system with a single CPU, we refer to that as multi-programming. And if we have many processes in the same computer, and there are many processes running, but there are processors, many processors on the same computer, we call that multi-processing. Now, just want to mention that if a number of processes are running and they need to communicate with one another, they're not permitted to communicate inside while they're executing inside main memory. No process is allowed to go to another process main memory and get some information from it or put some information there. It'll be terminated immediately. There's a protection, as we did in memory management. So most processes, the way they communicate together, the way they exchange information, is one of them writes to a file outside kind of the computer, and the other one opens the file and reads from it. But that is a very slow operation. You know, CPU and processors, they operate at this, almost at the speed of light, but if you're using a hard disk, then you're using a mechanical device which is so primitive, so slow compared to main memory. So that's not a nice way, that's not a very efficient way for processes to communicate. So they came up with this idea of using, instead of multiple different processes, they use the same process, but it kind of spawns itself. It makes another process of itself on the same space in memory. We call it a thread. It's like a process have a baby. We call it a thread. They call it a child of that process, but we'll stick to the word thread. So a thread from a process is another copy of the process unto itself in the same space in memory. So you don't even copy it, it's just the same space in memory, and you have another process executing it. This is very much like in a kitchen, you have the recipe to cook something, and that recipe is on the wall in the kitchen. That's like the code of a program. And you walk in and you start following this code. You're the process. You're actually executing that code. But then when you reach line 7 or 8 or 9, another person walks in and starts executing the same code, cooking the same meal. And they follow the same instructions. So they are using the same code, but another person is starting a cooking operation. Maybe a third person comes in. These are what we call threads. They're using the same code, and they're saving, instead of separate process running in memory and needs its own space in memory, we're using the same space. So it's a very, very efficient way of execution, of running many processes, even though we don't call them processes, but they are actually processes. We call them threads, and they are identical. The first process and the second process and the third thread and the fourth thread, they are identical. They use the same code. The only difference between them is the ID. We give them a different ID. Every time a new one starts, we get a new ID. But now we can have multiple processes running, and they all have access to the same space in memory. And therefore, one go to X and put X equal 5, the other one can read it immediately. Or they can have an array or a queue, one puts some information on one end, the other one can read it immediately at the other end at almost the speed of light. And that's the quickest way any processes can communicate together. Remember, we call them threads. And that's very efficient. So if you have 5 or 10 of them running, they're saving us a lot of memory, because you're in the same space of memory, and they can also communicate. So these are advantages of using threads when programming. Instead of having 5 separate processes, they take 5 spaces in memory. No, we only have 1 space in memory, and the 5 of them can execute it. And they have many other advantages. When the thread does the contact switching with another thread, we take the CPU from one thread to another thread, it's faster than taking it from one process, giving it to another process. So it's extremely helpful in so many ways. It has so many advantages. Quicker to switch, do contact switching, and quicker to communicate. They communicate almost instantly, and they save us memory. So it's a fantastic way of programming. But they have a little problem. And that's the problem now we're going to talk about. Normally, there's no problem executing any part of the code. Remember, they're running the same code, and they're executing the same code at different parts of it. And it's okay to execute even the same line of the code. But there are some parts of the code that say, oh, you better not, only one process should run this, not more than one. So again, like in the kitchen, you can both, 2 start at the same time. This one say, beat the egg, the other one is beating the egg. They're both beating eggs separately and they're fine. But maybe if you put the stuff in the oven, this one says, turn the oven to 300 degrees, and this one say 100 degrees. Oh, it's going to cause a problem. Maybe because there is one oven and there's one setting. So if one of them sets it to 300, the other one is going to lose their meal for maybe burnt or something. Okay, so there are parts of the program cannot be executed together. And that's what we call the critical region or the critical section. So that's what we are going to be looking at today, is the problem of the critical regions when we are running multiple processes in a parallel processing or multi-processing environment. So let me open the lecture notes and continue from here. Any questions so far on the concept, on the idea? Good. Lecture notes. And here it is. Oh. So we refer to this as concurrent programming. Concurrent programming processes are executed simultaneously, and they have access to each other's memory, and they can exchange information. And they found that they're a really nice and helpful way of programming. It just simulates manufacturing. For example, a factory has a number of machines. One of them can maybe, I don't know, takes raw material, clean it, and then pass it to the next machine that will actually form it, and the next machine that will filter it, and the next machine that will bottle it. So a number of processes can be working in sequence and in kind of synchronization with one another. And they can, that's how most factories would work. Like a car manufacturer will probably start by having a chassis, and they put wheels on it, and they keep pushing that car. Somebody puts the door, somebody puts the engine, the next process or the next machine puts something else, until eventually at the other end you have the product. We have something similar in programming, where maybe a process, if I say to you, give me maybe the average of something, you might need to generate maybe random numbers or generate prime numbers. So we have a process generating prime numbers and giving it to the next process. The next process does something else with them and pass it to the next process until you get the end. So that's a very nice way of programming. And what it requires is these processes need to work together. And when they need to work together, sometimes they get out of tune with one another, and we need to keep them in tune. And we call it synchronization. So there is a synchronization problem sometimes, and that's what we will look at. And how do we solve out the synchronization problem? And I told you about the critical section. That's one example of those problems. You can run the same code, guys, but any part of the code, but those 2 lines or 5 lines, only one user. We wanted to use only one user. Just like, let me go straight to that. Let me share the first thread. We've already talked about this, and I'm going to just extend it today to the next section. So today I'll be looking at 3 of those solutions to the problem of lack of synchronization, or the problem of the critical section. And that's what it is really. If, for example, in a park, you have the whole park is shareable, that means just like our program, you go in and you can execute any part. But there's one part, say in this example, in our park we have this pool of water with this kind of piece of timber that's going across it, but it's only enough for one user. So if 2 users try to use it or more, that's a problem. The rest of the park, everybody can use. In any group of people, doesn't matter. Share it at the same time. But this particular section, we call it the critical region. That means only one user should use it. So we should organize, maybe have a sign or a traffic light or whatever tool that we're going to have. And these are the tools that we'll be using. This is another example of a critical region where if you don't control this, maybe this lane or this bridge can only allow 1 car to pass through. 2 cars come in the opposite direction, they won't pass. So we need to have a better control so we don't get delayed or get problems. And there are 3 tools used: test and set, wait and signal, and semaphores. And we'll look at the 3 of them. So we've already talked about test and set. But test and set is simple. Just have a sign at the start of the, for example, if we have this room, we get to the real example. The aeroplane, we have an aeroplane, everybody can mingle and walk around aeroplane and sit in any way they like. But if there's a toilet, and that's a critical region, should only be used by 1 user. So how do they control that not people being overwhelmed or inside the toilet? They have a switch, and they have it on the outside the door, and it says, just to mark this, says busy or free, or a traffic light. It's like a green light or red light. If you see green light, it means okay, it's free, you can go in. If you see the red light, that means somebody is in there. So simple. The idea is very simple. It was used by trains in the old days. And trains is just another example of the critical section. When train networks started expanding, they'd done a bit of saving by sharing some of the tracks. And by sharing some of the tracks, they started having accidents. And they consider that part, the part of the track that gets shared, they consider it a critical region. So they solved it by having a traffic light or a signal at each end. Before getting into the critical section, they had this device or this locking mechanism. If it's green, it's light, or it's a handle. And if the handle is up like this, that means don't go. The critical section is busy. And if the handle goes down, that means the critical section is free. You can go. So a train driver approaching from either side, they see the green light. They say, oh, the track is free. The critical section is free. Let me go in. So they hit a switch beside the track right here at the start of where the driver can reach it. And they move that lever, and that lever puts the handles up and turns the lights red, telling everybody, do not go in. Remember, trains cannot see one another until it's too late sometimes. They start speeding up, and then they see, oh, there's only 50 meters away or 100 meters, and they put the brakes on, but they can't stop on time, and they end up crashing. So they have this signal to indicate to them, hey, there's another train using the critical section. So if it's red, if a train approaches the critical section, they see the red light. They know there's a train there. They can't see the train, but they know a train is using the critical section. So they stop and wait. And then they keep checking. So the train driver might even get a break. It might take 20 seconds, might take even 2 minutes if the train is coming. Some trains, they switch them on maybe 2 kilometers away. They're real slow. So maybe a waiting train driver can make a cup of tea. And every now and again he looks and checks the light. Is it green yet? No, because when that train that's in the critical section, when it leaves, it will hit the switch to turn the lights off or turn the green lights back on, indicating I'm finished, I'm out of the train. And now the waiting train can look and say, oh, the lights are green. Good, now I can go. They hit the switch and turn the lights on. This technique is called test and set. That means you look at the signal when you're approaching the critical section, whether it's a train track like this, the critical section, or the toilet in an aeroplane. You need to check the signal on that at the start, at entrance to that place. If it says it's free, you can switch it on, make it busy, and go in. Or go in and make it busy. And that will stop anybody else coming in, because everybody must follow the same rule. When you're approaching, check the signal. If you see green light or it says free, you can go in and make it busy. And when you leave, you have to open that door or unlock that lock, and you make it green or indicates that it's free. You know, in computing, we say 0 and 1. If it's 0, that means there's nobody in there, it's free. If it's 1, it's busy. So in our programs, they look, is it 0? Yeah, we'll turn it to 1 and go. This is exactly the name. Test and set. You test it. What value are you? 0? We'll turn it 1. So that's the first technique that's used. It's very simple. You look at the light, if it's on, if it's or 1 and 0, or light on and off, or busy and free, whichever the technology or the term you prefer. So this is called test and set. Just so you'd remember the name. Test, that means you look and test that value. The flag. Is it busy or is it free? And if it's busy, you can't do nothing. You have to wait. But if it's free, set it to become busy. See the idea? That's the name. Test and set. Test it. If it's 0, turn it 1. That means if it's free, make it busy. And you go in. You booked it, you stay in there for as long as you like. When you finish, you come out, you turn it free. You turn it to 0. You put the light green. So the next person waiting, they can check it. And that's how test and set works. So let's look at it, how it works. Here's the code, here's the program. This is actually in computing. You have a program. Most of it, it's no problem. 3 processes can execute exactly the same lines without any problem. But we have this gray part here that we say, no, only 1 process should go in. If there's one already executing that, don't go in. That's the one we want to protect. We call it the critical region or the critical section of code. So if there are three processes running, and they are approaching, first, how do we start? We start by saying, at the very beginning, no process is running. This starts, and we indicate that this flag is free. The critical section is free. So we put either indicated by 0 or a green light. That's the initialization. So the test and set, you need to know that we start with value 0. And you know what value 0 means? What does 0 mean? It's free. There's nobody in there. 0 number of users are in there. So these are threads that can work together. Sometimes I'll say process. The more accurate term is threads, right? So they are threads running because they can execute same code and access the same variables. Processes cannot see the variable C if they're separate, different processes. But now we have one flag that control that all the threads can look at it. But if I use now the word process, it's okay. What I mean is a thread. So anyway, so we have a number of threads or processes executing here. They should not. When they come to the critical section, we want to make sure, you want to make sure as a programmer, only one goes in. So you put this flag and you put those 2 lines at the start of the code, and you say, what does those 2 lines say? As long as the place is busy, stay here. Keep checking it. This is, you're actually checking C, is C0. That's what the question here. That's what your program will be doing. What value is C? Is it not 0? Is it 1? That means it's busy. Well, don't go in. Just keep checking. You keep repeating. While means keep doing this. Keep checking. As long as it's not 0, keep checking. So if it's 1, it's busy. Keep checking, keep looking, keep looking. In fact, they go to sleep a little bit and then look. They don't continuously do it because that's a problem. Every time you look, you use the CPU. That's an expensive way of looking, checking all the time. And you're going nowhere. They call that busy wait. So if you're asked, what's a busy wait? Busy wait is not a good thing. That means you're doing nothing, but you're wasting resource. You're wasting the CPU. It's like you're a car driver and you're waiting to collect your friend. You pick your friend and you're going for a trip. And you go and you pull outside the house and your friend should come out. The engine is running, you're burning petrol, and your friend takes 20 minutes. You wait for 20 minutes with the engine running. We call that a busy wait. That's really expensive way of waiting. You should turn the engine off. But that's the way this thing works. Keep checking. Sleep a little bit and check again. So every time you check, you're really consuming CPU time. But anyway, that's how we start. We start with that initial, the flag indicating that the critical section is free. Now a process comes in. It checks the flag. This is the test and set. Test it. Is it 0? Yes. Turn it 1 and go in. Right? So that's what this line here, the second line, C equals 1, that means turn it, set it to 1. So it's so simple. If you forget how it works, think of the toilet. Is it free? Yes. Go in and lock it. Lock the door. If the signal outside will say, hey, there's somebody is there. Somebody, it's busy. That's exactly what the door on the toilet in an airplane will have the word occupied or busy. And when you leave, when process 1 leaves, it's just, well, hold on, this one before leaving. Well, if process 1 leaves, it will turn that flag green. It's like you leave, you open that door and leave it unlocked, indicating it's free. But now process 1 has not left. Process number 2 comes in. It finds it busy. It cannot go in. So it will go into a little sleep and test, repeating that. So sleep for a little while and test the flag. It looks at the flag, just like what the train driver is doing. He'll be chatting with his friend, and then every now and again looks at the light. Have a kind of drink or something to eat and look at the light. But in our case, it's going to be 100th millionth of a second or something. Sleep and then check the light. And so instead of checking it all the time would be way too expensive. Even this way is expensive. But process number 2 is checking. Go sleep and check again. If that light, if it finds the light green, it will go in and turn it red and stay in the critical section. Now another process comes in. Remember, process 1 is still in the critical section. Now process 3 arrives. What do you think it will do? But just the moment, just before this moment, process number 2 just checked the flag. It said it's red. It went to sleep. The moment it went to sleep, process 1 left. When process 1 left, it turned the flag free, unlocked the door, and left. Process number 3 just arrived at the right time. It should be process 2 should go in, but process 2 is asleep right now. For a very brief period of time, it goes sleep. That's unlucky for process 2, because process 3 arrived at the time when process 2 was asleep and process 1 has just left. The light is green. Process 3 checks it. That's the test and set. Test it. Yes, it's free. We'll go in and make it busy. So process 3 now goes in. And process number 2 will wake up and look and find the flag is still busy. It just missed its turn, but doesn't know that somebody has left and another person has gone in, or another user or another thread has gone in. So now we've just seen the 2 problems of test and set. Test and set was a nice technique, but it has those 2 problems. Busy wait and starvation. Starvation, if a process misses its turn, and if it keeps missing its turn, then it could end up sitting there for a long time, which is not fair. So it has those 2 problems. Starvation, if you're asked, how does starvation happen in test and set? You say every time the process that's waiting goes for a little sleep and then test goes for a little sleep. If that moment, when it goes sleep, if the process in the critical section leaves, it will make the flag appear, telling us that the critical section is free. Any approaching process can go in while this process is asleep. So it's the fact that it has sleeping and checking. It's not continuously checking. Of course, continuously checking is another bad thing, because we call that busy wait. So even process 2 here will be using the CPU every now and again, and that's a high cost. So that's how test and set work. Somebody asks you, what's test and set? It's a locking mechanism. It's just a variable. It can be a bit. So efficient. It's not expensive itself. 1 bit can control access to a place. 1 bit. It's just like a lamp outside a door. Switch it on, that means somebody in there. They use that in radio stations and television stations. If they are recording, they hit the switch, red light goes on the front of the door. That means we're recording now, don't come in. Nobody from the outside is to come in. When they switch it off, that means anybody can come in. It's not a critical time. But here we're controlling critical section. So test and set, just from the name, it's testing, it's looking at the number, test it, and if it's 0, turn it to 1. That's what the word test and set mean. So if you need to explain it, just remember it or try to think of it logically. It's a protection that's used, it's a locking mechanism used for a critical section, to control access to a critical section, that only allows 1 user to go into that critical section. But it's not very efficient. It has 2 problems. Do you remember what those 2 problems are? Critical section and busy wait. Right. So that was used in computing earlier on in computing, but then they fixed those 2 problems. Okay, let's see what happens here and finish just to see how it works. Now, process 1 left, process 3 approaching. It shouldn't get it in there, but the timing is perfect. It see the flag is green. It tests it. It's free. Set it to 1 and go in. So now process 2 missed its turn. After a while, process 3 left. It turns the flag free. Now process number 2, after a little nap, it will look, check, and say, oh, the light's free. Let me go in. And it goes in. And when it finishes, it will unlock that, reset that flag. So that's how test and set works. But it has those two problems: starvation and busy wait. So in computing, they improved it with this new technique, and it's called wait and signal. Wait and signal. Wait and signal, there again, they said, approaching a critical section, we will have two functions. We'll have a function called wait, and there it is, one line of code, and before the critical section. And another function called signal, again, one line of code after the critical section. So it's very easy from software point of view to control a critical section. One line of code, maybe two at the most. But now we call them functions. One is called wait. They call it wait because you're testing. It's the same as test and set, but they just call it a different name. Wait, they call it wait because maybe you have to wait. Am I supposed to wait or go in? Well, it depends, obviously, if the critical section is busy or free. So it's still testing and setting. And at the end, when you finish, again, most likely you'll still have to switch the critical section to be free. But they've added a queue now. Remember the previous technique, the test and set, the waiting process, this waiting process, think of the airplane. Again, you walk, you need to use the toilet. You walk towards the toilet, and you look at the toilet, and you see the sign on the door says occupied. So you have to wait. So you might turn into the window and start watching the clouds. There is no specific place for you to wait. While you're kneeling and watching the clouds, maybe the person in the toilet has left. You just haven't checked again. And someone else approaching, they went in. And then you pick yourself off the window and look again, and you find the door is busy. You just missed your turn. And the reason, someone else was able to get in ahead of you. There was no specific way of waiting. But now with the newer technique, they said to solve that problem, let's have a queue. If you come in to a critical section and you find the critical section is busy, go into the queue. Like there's few seats there, you go and sit at the first seat. If another person comes in, they sit in the second seat, and so on. And the way that we used to miss the turn is just because whoever leaves, they switch it, they make the place available, free. They said, don't do that, because a new person approaching might get in there. So there are a number of issues. And the busy wait, they said, in the previous technique, you have to keep checking. Is the critical section free? Is it free? Is it free? No. In computing, we don't do that anymore. Any critical section, any resource you want, any request you only put it once. Don't ask for it again. If it's available, we'll give it to you with one request. If it's not available, you should go sleep, and when it becomes available, we'll wake you up. So in computing, we never keep checking something. That's not an efficient way of doing it. So if you ever write a program, don't use that approach. While C is less than something, you keep checking. Don't do that. Just do an if statement. If it's not there, I'm going to go sleep. I'll use nothing. Wake me up when it's available. The operating system will wake you up. So this is what they decided to do at the end. And how do you wake up? They called it a signal. It's just like an alarm. Like you need an alarm in the morning to wake you up. Or you ask somebody to give you a phone call. You go to sleep and somebody's going to ring you. That's the signal that we're talking about. So they call this, the first one, they called it wait. So when you approach, you might have to wait. You might have to go to sleep. They call it wait function. And the last function is the one they said, when you leave, you are responsible to wake anybody who is waiting. So you need to see if the queue has anybody. So this is now how the wait and signal works. Similar to the test and set, but with some Fantastic changes. Simple, but that's very effective. First, remember now we have a queue. We didn't have it before. And the queue, we need to know how many are in the queue. 0, 1, 2, how many are waiting? If 0, you know there's nobody's waiting. Right, and that's how we initially start. We start with the flag 0. What does 0 mean? With this, so with those two techniques, the test and set or the wasteland signal. The main variable, C0, means the critical section is free. But now we have a queue as well. If you see 0 in the queue, that means there is nobody waiting. So right now, there's nobody waiting, and the critical section is free, and there's nobody waiting for it. That's how we start. We call it initialization. And then we start running. So now imagine there are a number of processes executing, and there's one of them approaching the critical section. Before getting into the critical section, you must execute the wait function. The wait function is just one line. And as you can see, it's not while, it's F. While, that means keep doing it. No, F means do it once. If the critical section is busy, if it's 1, you're testing it. Is it 0 or 1? If it's 1, you have to wait. You have to go to sleep. And we'll wake you up later. If it's 0, then turn it 1 and go in. This is exactly like the test and set. There's no change here. So it's very simple. You're approaching the toilet in an airplane. You check, is it free? Yeah. Well, go in and hit the lever and it becomes busy. Now, that's what P1 will do. It found that the place is free. The critical section is 0. That means there's no one there. Go in there and turn it to 1. That means now it's busy. So nobody else will be able to read. It's like the toilet. There's a person in there, and outside the door it says busy, occupied. So any coming person, they have to wait. But now we have a special way for them to wait, the queue. So why? So they won't miss their turn. Now, process number 2 comes in. It checks. Again, it tests the flag. It's busy. That means I have to wait. But now it waits. It goes to sleep. Remember, the previous time it was testing and sleeping, testing and sleeping. No, just go to sleep. But sleep in the right place, in the first line, the first position in the queue. And see the number of the queue. How many now are in the queue? 1. Remember, just before process 2 went in there, queue equals 0. That means the number of processes waiting in the queue in line, there's nobody waiting. But now we have 1. And every time somebody comes in, you increment it by 1. And every time somebody joins the queue, we add 1 to it. Everybody leaves. Every time someone leaves the queue, we decrement it. So there it is. Now process number 3 approaches. What happens now? It checks the flag. It's busy. Goes into the queue, and it's now in the second position. So now we have control who's going to go next. Now, this is the only difference. This is the difference now in process between wait and signal and the previous technique. When you leave, when a process leaves, we used to just go and switch the place free. We tell them the place is free. But if we do it, if we do that, if we turn this flag to free, any coming process will get in before 2 and 3, before the waiting process. So we don't turn the flag free. What you do is you first, before you switch that flag on, check anybody waiting in the queue. If there's anybody waiting, don't touch that flag. Let it appear busy. So even now, at this point, if another process comes in, it will check the flag and say busy, it will join the queue. So it will never kind of jump its turn. So now we can see that the queue, see it says, see the signal function, the line says, if there's anybody in the queue, that's if queue is greater than 0. That means how many people are waiting in the queue. If it's more than 0, yes, it's more than 0, there are 2. Well then, give them a signal, wake them up, wake the first one. In fact, you don't have to wake it, you tell the operating system, listen, do this signal. It's like your mobile phone. You give them a call and you leave. So you wake the first person in the queue. So process number 2 wakes up and gets straight into the critical section. Doesn't have to do anything. The critical section is still busy. It just continues into the critical. And remember, it's waiting, and that process is really waiting at this line. It's waiting here, sleep right at this spot. So the moment you let it go, it's straight into the critical section. So now process number 2 is it goes into the critical section. Process number 1 is gone, is left. Now either a new process will come in or process number 2 will leave. Process number 2 will leave. Will it turn the flag free? Will it tell us that the critical section is free? No. First, see the line says, check, is there anybody in the queue? This question here, if Q is greater than 0, it's like asking, is there anybody waiting? That's what it means. If the number of waiting is more than 0, that means there's 1 or 2 or 3 waiting, well then signal them. So it will signal number 3. And number 3 will go into the critical section. Now when number 3 leaves and checks, is there anybody in the queue? There's nobody in the queue. But in that case, if there's nobody waiting, well then turn the flag into 0. Make it show that it's free. So this way, no process will be checking and checking and checking the flag. You only check the flag once and then you go to sleep. But how are you going to wake? Whoever is in the critical section, when they leave, they'll give you a signal to wake you up. And this worked perfect. This is better than the test and set. It's so efficient. Nobody's going to jump your turn. There's no starvation. So it overcome those 2 problems. How did we remove starvation? By having a queue. You don't just wait randomly, you go into the queue. And the person leaving, they don't just turn the flag on or make the place look it's free. Check first, is there anybody waiting? And how did we remove the busy wait? So the busy wait, we got rid of it because you only check once. See this F in the loop here? It says F. You do your check once. Remember, I just bring you back to the set, and this is the test and set. See the line? While. That means while is repeating. Keep doing this all the time. And every time you check the flag on or off, you're using the CPU. So here we say, don't ever use the CPU. F, check it once. If it's free, go in. If it's busy, go to sleep. Don't check it again. When it becomes free, we'll signal you. Okay, you understand? Wait and signal. Wait, that means you wait beforehand if the place is busy, the critical section is busy. And the signal means before you make it free when you're leaving, check is there anybody waiting, and if there are, wake them up first, give them a signal. And this is beautiful. This is the most efficient, and it's so secure and safe, and it works, and it protects a critical section. It will never allow any more than 1 process. And it's your responsibility to look at some part of the code if you start having problems and say, oh, that's critical section. Every time 2 processes go in there, I end up maybe my code is terminated or something. Well, then I consider that critical section. I put 1 line, the wait function before it, and the signal function after it. 2 lines of code, and they'll protect your critical section. And that's great. Until they came to a situation where they said, guys, we have a critical section, but it doesn't mind if 2 go in, but no more than 2, or 4, but no more than 4. Because when they started programming other real life applications, for example, you want to simulate or do a program for a petrol station. How many cars are served at the same time? It depends on the number of pumps. If there's only 1 pump, that means we only allow 1 car. The rest of them in a queue and 1 car at a time. But if we have 2 petrol pumps, we can actually serve 2 cars. If we have 4 pumps, 4 cars can come in, serve them simultaneously. Car number 2 leaves first, another one can come and take place. Car number 4 leaves, and so on. So there are other systems that require a different model. This wait and signal will not work for them. This will only work for 1 user of a critical section. So somebody came up with what we call the best optimal solution, and they call it a semaphore. So a semaphore is same as the wait and signal. It's another mechanism, but It will work for any number we want. If we want only one user, it's the same idea. If it works if we need 3 users to go into the critical section, it will work. And how does it work? It kind of works the opposite. Easy to visualize how it works. If you understand it, you'll never forget it. It's so simple. And if you don't understand it, it's so difficult to understand. So try to, just for the next 10 minutes, concentrate. And anytime you hear the semaphore, think of a hotel. Just think of the hotel as the critical section. Now, a semaphore, for example, in this example, there's a hotel with 3 rooms. What does that mean? It means we can allow 3 persons in there. No more. 1 person, okay. 2, okay. But 3 is the maximum. If there's anybody else, they have to wait. So this is what we want to think of now, the semaphore as an implementation of this. So this is how it works. When we start in a hotel, if the rooms are free and there are no customers in there, they'll have the keys hanging in reception. So that's the number. That's the C that we use. That's the integer number. It's the keys that really... So when we start at the beginning and there's nobody in the hotel, you should see 3 keys. So we start with the number that we want the maximum. So if I say to you, we need to have a critical section that allows 5, then you must start with 5. Your initial value is 5. Remember, in the older one, 0 means it's free. Here, 3 means it's free in this example. Now, first customer comes in. One customer comes in and say, hey, I need a room, right? So you look and there are 3 rooms, 3 keys. So you take one of them, we know if the key is there, that means the room is free. We give them the key and the first customer go to the room. Now that we have 2 keys, another customer comes in and say, can I go into the critical section in the hotel? And we look at their 2 keys. Yeah, we give them 1 key and go. So now we have 2 customers who have 1 free room. A third person comes in, we can give him the 3rd key. Now all our rooms are free. How many keys do we have? 0. So when you see 0, that means we're full. We can't take any more. Another customer comes in, want a room. We say, sorry, we're full. You'll have to wait. And there's a place where they can wait. There's a queue. So they can sit here on that couch waiting until one of the customers leave. This is how a semaphore works. So when you start, you don't start with 0. That variable, you start with the maximum number allowed in our critical section. And every time a customer comes in, we decrypt it. Not like the other one, switch between 0 and 1, 0 and 1. No, this one, every time we get a customer and we can accommodate it, we reduce the number. When we are 0, we can't let any more in. Okay, that's the idea is so simple. So let's see how it actually works. Here it is. This is the idea of a semaphore. Is it semaphore? Yeah. Hold on, we should have started with a number here. Yeah, okay. So here's a semaphore. We have a critical section that can allow 2 at any time. So we start with S for semaphore equals 2. That means our critical section can take 2 users. Maybe it's a petrol station that has 2 pumps, or maybe a room in a hospital that has 2 oxygen pipes. We can only move 2 patients in there. No more patients can go in there. Right? So it has a queue. It's like the wait and signal. So it has a queue for waiting, and there's nobody there now. When there's nobody, we have a number. If we have a 0, that means we are busy. The opposite of the previous one. This is the major difference between them. Just think semaphore is like a hotel. If you see the keys, that means we have plenty of rooms. If you see no keys, 0 keys, that means all the rooms are gone. And you have to wait. So now, first process comes in. So this is what we need to write the code. Now the functions, this system was invented, or the guy who invented this is a Dutch guy. So he used P and V. I don't actually remember what the Dutch word for P and B, but think of it as wait and signal, similar to that. Right, so we run the P function. The P function is simple. It says, if the place is full, you have to wait. So it checks if S equals 0. Remember, 0 means full. If S is 0, then wait. If it's not 0, that means we have 3 keys. In this example, there are 2 keys, remember. We have 2 keys. So take one of them and go in. So this guy takes one of the keys and goes in. So and see, S was decremented to indicate S is 1. So we have 1 key left. This is like a hotel with 2 rooms. So we have the 2 keys. First customer came in, took the first key. Now, another customer comes in. Can they go in or not? Yeah, they look, there's another key. We give them the key and they go in. Now we have 0 number of keys. That means we're full. See the opposite? The last one was 0. That means we're free. We're free. There's nobody in the critical section. Now, when we have 0, that means our critical section is full. Now, if another process comes in, it has to wait. It's like you going into the hotel and you look at the reception and say, sorry, we have no keys. Look, all our rooms are gone. You'll have to wait. So this guy's sitting, waiting in reception, in a queue. So we have a queue. See, P3 is sitting there now, and the number of users in the queue is 1. So we have somebody waiting. The rest of it is like the signal. So let's say one of these processes leave. They don't have to leave in the same order, whatever it is. Let's say process, oh, another one coming in. So process number 4 come in. Can it go into the critical section? No. The critical section is busy because, see, the 0 shows it's busy. There are no keys in the hotel. That means the rooms are occupied. So it joins the queue. So now we have 2 processes in the queue. Process number 2 left. Remember, it wasn't the first to come in, but it left. It doesn't matter who leaves first. So process number 2, it's like petrol station with 2 pumps. 2 cars came in. Car number 1, car number 2. Maybe car number 2 will finish first and leave. That's what happened here. It doesn't matter which car leaves first. It doesn't matter which customer, which process, or which thread leaves first. Okay, are these threads or processes? Anybody remembers? Threads, because threads can see each other's variables and can work together. Processes cannot. You cannot do this with processes in their memory. Each one of them can only see its own memory, but threads. Okay, but let's keep going. So process 2 left. What do you think it will do? It will check and say it will execute the V function. Remember, approaching, you must execute the P function. Leaving, you must execute the V function. The V function says, check, is there somebody in the queue? If the queue is greater than 0, that means there's somebody waiting. It's like you live in a hotel with the key in your hand. Reception is there, but you see 1 or 2 people waiting. You go to the first person and you give them the key and let them go up to the room. You don't, if you leave the key in reception, then somebody walking in can take it, a new process. We don't want to miss turn. We don't want starvation. So signal. So you actually signal process 3. If there's nobody waiting, okay, we'll give the key back to reception and we increase the number of keys. But see, the number of keys, S, is still 0. It still says this hotel is busy. Even if somebody comes in right now, they cannot go in as a replacement of P2. They have to go into the queue because the flag says the place is full. Even though you're leaving, you're about to leave, but you don't put the key back in reception, you give it to the waiting process. You don't, virtually give them the key, but you just tell the operating system signal that queue. So they'll get the first process to go in. So process 3 goes in, and then after a little while, process 1 leaves. What happens here? Do we increase the number of keys? Yes? No, we don't, because somebody's waiting. See, you have to check. The V function say, check the queue. Is there somebody in the queue or is it 0? Oh, there is somebody in the queue because we can see the number 1. So there's 1 person waiting. Well, then give them the key and they can move, signal them, and they can move into the critical section. So now we have two processes in the critical section. Nobody is in the queue. What happens now? So like in a hotel that only has 2 rooms, there are 2 customers in the rooms, there's nobody waiting. If one of these guys leave, what happens? You check, is there anybody in the queue? No. Well, then give the key back to reception. They'll hang it now. You can see the number of keys has increased to 1. So if a new customer comes in, they can go straight in. And then number 4 leaves. Also, there's nobody in the queue, so we leave the key back in reception. Now the reception has 2 keys. So we actually controlled this critical section. Only 2 can go in. And this is how a semaphore works. Anytime you hear the word semaphore, think of a hotel. Anytime you hear the wait and signal or test and set, think of the toilet in an aeroplane. Right. This is a table that shows what happens that time, that what we were talking about, but it's placed in a table format. So the table shows on the left here, stages, time of, the next moment of time, the next millisecond or second or hour or whatever. If it's a hotel, the next day. So let's look at a real example. See, this is how you'd get a question. The last 2 years, this question appeared in every paper. So keep an eye on this. Make sure you understand it. It says here 2 threads. We have 2 processes or 2 users coming in. That they arrive. Why is this here? Yeah. Into a critical section or a critical region. What? Somehow it just gave me a problem with audio recording is not working. Okay. And in this program, there's a critical section. And at time 1 and 3, respectively, these 2 processes arrived. That means this process arrived, if there was a hotel, this one arrived on day 1 and another one arrived on day 3. If it was CPU, we'd be talking about milliseconds. This one arrived at millisecond 1 and the other one is 3. So at the left, you have the time. So we'll have a 0, 1, 2, 3, all the way to whatever number we need. At 0, you always need to specify what's the initial value that we start the semaphore. See, the last column here is the semaphore. Semaphore is a value. What value do we start with a semaphore? Whatever the maximum number. So let's see if the question here specifies. It says the critical section is protected by a mutex semaphore. The word mutex semaphore or binary semaphore, it's just a semaphore, but only allows 1 user, the maximum. So you need to know that. Mutex comes from the word mutual exclusive critical section. That means only 1 user. So if the question says, I'm having a semaphore, it's a mutex semaphore, that means only 1 user goes in, without actually telling you it's 1 user. But similarly, if you hear the word binary semaphore, it means 1 user. If it doesn't say that, well, then it tells you 3 maximum users can go in, or 2, or 5, or whatever the number is. But if it's or 1, it might tell you this semaphore will only take 1 user. But it's just another way of saying it. It might tell you this is a mutex semaphore. So just remember, mutex means 1 user. And it comes from the word mutual exclusion. I mean, it's not shareable. Okay, the critical section is protected by mutex semaphore. We call it S. Trace the event occurs while all processes pass through the critical section. So we start at time 0, there's nobody. So what time do we set the semaphore? We set it at 1, because semaphore is always set at the maximum number allowed into the critical section. Okay, do you understand this? With the previous systems, we start with 0, indicating this is free. Now, 1, it means the critical section is free. It's like a hotel with 1 room. There is 1 key in reception. You always, in semaphore, you start with the maximum number you are allowed in the critical section. So now we start with number 1. At time 1, we know you can immediately, this one arrives, you can put J1 here. It's arrived at time 1, and it says the other one, J2, arrives at time 3. So we just write it immediately. So this one arrives at time 1, this one arrives at time 3. J1 comes in, okay, and notice each of those threads will spend 4 days. Like each one of those customers will stay 4 days in the hotel or in the critical section. So let's start. So process number 1 comes in. If it comes in, it must issue the P function. Here it asks you, is this issuing P function or V function? The P function is issued when you're arriving. When you're leaving, you must issue the V function. The P function is checking, is the place free? Can I go in or will I wait? So J1 arrives, it will issue the P function. The P function says, is the critical section free? It will look, it's like you arrive into a hotel that has 1 room. You look at reception and there's 1 key. You take it, you go into the critical section. So now J1 is in that room, in the critical section. And the number of keys, 0. Now, time number 2, nothing happens. Because we know this guy here will stay for 4. Now, once it goes into the critical section, it will leave at what time? It's like you arrive at time 1, you're going to stay for 4 days. 1 plus 4 is 5. So J1 is going to leave at day 5. Okay, so you're right. You go straight to day 5 and just put down J1 VS. That means J1 will leave. That's exactly what they do in hotels. You come in, you arrive today. When are you leaving? You tell them I want to stay 3 days. Today plus 3, and they write what date you're leaving. So it's like here, you're really writing what date J1 is leaving. How do we know? We know when it went into the critical section and how long it will spend there, 4 milliseconds. Remember, J2 also will need 4. The next process will need 4 milliseconds as well. Even though it arrived at time 3, but it didn't go into, well, see. So now, we go to time 3. J2 arrives. It issues the P function. That means I want to go into the critical section. Can I go in there? Remember, this is a hotel with 1 room. We already have 1 customer in that room. You look at the number of keys, 0. That means we don't have, you cannot go in. So you have to wait. So it goes into this part here. This is the queue. So you have now the positions. This is who arrives, what function they do, who is in the critical section. This column is critical section. This column is the queue. So we have now process number 2 waiting in the queue. Process number 1 is in the critical section. The number of keys left is 0 because we already, the key is held by J1. Day 4, nothing happens. This one is still in the critical section. This one is still waiting. At day 5, we know J1 is going to leave. So it issues the V function. What does it do? Does it leave the key? No. Checks, is there anybody in the queue? J1 is leaving. It looks, is there somebody in the queue? Yeah. J2 is in the queue. So now it gives the key to J2. J2 can go and take that room, and still there are no keys. It's like you give the key to the waiting process. J2 is waiting. Give the key and you say, go to the room. So you don't give the key back to reception as long as somebody is waiting. So J1 has left. J2 got into the critical section at time 5. Just got into the, even though it arrived 2 days earlier, but it's been waiting for 2 days. It only got into the critical section at day 5. You know what day it will leave? See, it will stay in the critical section for 4. Up at the top, they tell us it will need the critical section for 4 units of time, 4 milliseconds. But here, hotel, we say 4 days. So if it arrived at day 5, plus 4 is 9. So we know it will leave at day 9. So we go straight to day 9 and say, okay, J2 will be leaving at that time and we put VS. So day 6, nothing happens. Day 7 and 8, nothing happens. Day 8, J2 leaves. It issues the V function. The V function says, is anybody waiting in the queue? No, there's nobody waiting in the queue. Well, then give the key back to reception and walk out. You think you can follow that? Or you can tell the story of that or fill this table based on this information that was given to you up there? If so, go ahead and do the next page, or so see if you can fill that. So get one that's empty and start filling it. That's the kind of question. That's the questions I put in tutorial and in practice. You need to be able to follow this table, fill it correctly to indicate who is going to be, how it's going to happen at which time. So I'll see you next week, I guess.